Okay, so these are going to be your half-life example problems. For half-life, we talk about the half-life of a substance like uranium, cobalt, radioactive elements that decay over time. So anytime we're talking about decay or growth or exponential growth, we're going to be using this formula right here. And I like to call it the PERT formula. So P is equal to P naught E to the RT, where P is your final amount, P naught, P0 is your initial amount, E is your E that we've been using, R is your growth rate or decay rate, and T is your time in years. Okay, so let's take this example. The half-life of sulfur-35 isotope is 87.1 days. How much of a 2-gram sample will remain after 100 days? So the first step when we're doing this is we always find our R. Okay? So if it says the half-life is given, that's half the initial amount. Okay? And we're looking for R. Your T is 87.1 days. Okay? Your P naughts cancel both sides, and so we're left with 1/2 is equal to E to the 87.1 R. So it's a simple exponential equation. We're going to natural log both sides. Natural log of E is 1. And so we divide both sides by 87.1, and we get natural log of 1/2 divided by 87.1 is negative 0.007958. You need to go a few decimal places on this, just because when you start dealing with exponentials and you plug it in, your error is going to be greater the fewer the decimal places you got. Now, once you find R, you're going to take it and you're going to do this equation again. Okay, so you want to know how much of a 2-gram sample remains. So your initial amount is 2. Your R is what we just found. And your time is 100 days. Okay, so plug that in a calculator. We're going to do our exponential first, so negative 0.007958 times 100. We're going to E it, so we do second E, and we're going to use the answer key. Okay, like that. And then we're going to multiply it by 2. Okay, so 0.902 grams remain. Okay, so pretty much every one of these problems is going to kind of follow the same procedure. Okay, one isotope of chromium has a half-life of 23 hours. How long will it take 50 grams to decay to 40 grams? Okay, so our first step is to find R. So we say P is equal to P naught E to the RT. The half-life is half the initial amount. Your R is what we're looking for, and T is 23 hours. The P naughts cancel, and so we're left with 1/2 is equal to E to the 23R. Okay, so we're going to natural log both sides. Okay, so we're going to divide, and we get natural log of 1/2 over 23 is negative 0.03014. Okay. Now from there, we're going to use P is equal to P naught E to the RT. And it says, how long does it take 50 grams to decay to 40 grams? So 40 is your final amount. Your initial amount is 50. We're going to plug in our R. And I'm going to solve for T. Okay? So I can cancel a 0 on both sides. Divide the 5 over. So we get 4/5 is equal to E to the negative 0.03014 T. Now, to solve for T, we're going to natural log both sides. Just like we've been doing. Natural log of E cancels. So when we put this in the calculator, we do natural log of 4/5 divided by negative 0.03014. Okay, so you get 7.4036. And we're in hours. Okay, so you need to make sure that your time units match, especially like weeks and days, years and days, that sort of thing. Okay, if 25 kilograms of a 100 kilogram sample of carbon-14 remains after 12,000 years, calculate the half-life of carbon-14. Okay, so this one we're going to work a little bit backwards. We're not given the half-life, so that's what we're looking for. So we say P is equal to P naught e to the RT. So our goal is to still find R first, okay? I have 25 kilograms remaining, initial 100 kilograms, E, your R, and after 12,000 years. Okay, so we're going to divide. We get 1/4 is equal to E to the 12,000 R. And we're going to natural log both sides. Like that. Okay, natural log of E goes to 1, so we solve for R. And R comes out to be natural log of 0.25 divided by 12,000. And you get negative 1.1552 times 10 to the negative 4 power. Okay. Now, we want to know what the half-life is. Okay, so we go and we say P is equal to P naught e to the RT. When we do half-life, it's half the initial amount. That's what half-life means. Your R, we just found. P naughts cancel. And so to solve for T, I'm going to natural log both sides. Okay, so we're going to divide. Now I need you to make sure you pay attention to this. So natural log of 1/2. Now I'm going to divide by my R, whatever that is. So negative 1.552. Now watch how I put this in, negative 1.1552. The way I put times 10 to the negative 4th in the calculator is I use second comma, the EE key, and I put negative 4. That's the way you should always input times 10 to the power in your calculator. I don't care who's taught you that, that's the way you should do it. Okay, so the half-life is 6,000.235 years. And I think carbon-12 or carbon-14 from UIL, I think they tell you to use 6320 is the half-life. So it's pretty close to what we're looking at. Okay. Next example says the half-life of carbon-14 is 6,000 years. How much of a 15-gram sample will remain after 1,500 years? So you're given the half-life. So P is equal to P naught e to the RT. 1/2 P naught is equal to P naught e to the R, and we're looking for R is and the T is 6,000. P naughts cancel, so we're left with 1/2 is equal to E to the 6,000 R. Okay, so we're going to natural log both sides. Okay, and so we get R is equal to, natural log of E goes to 1. So natural log of 0.5 divided by 6,000. And it's the same number we just did before, and it should be. Okay, now it says how much of a 15-gram sample will remain after 1,500 years. Your initial amount is 15. Your E, your R is negative 1.1552 times 10 to the negative 4, and that's after 1,500 years. So I'm going to do the exponent first. I'm going to multiply that number as already in the calculator times 1500. I'm going to raise it e, and I'm going to do the answer. I'm going to use the answer thing. Okay, and then I'm going to multiply it by 15. So 12.613 grams. Okay, last one. It says a fossil sample now contains 60 milligrams of carbon-14. There were originally 133 milligrams of carbon-14 in the sample. If the half-life of carbon-14 is 5730, that might have been the number I was referring to, 5730. If the half-life of carbon is 5730, find the approximate age of the fossil. Okay, so let's do half-life first. So P is equal to P naught, e to the RT, half the original amount. So if it was a quarter life, this would be 1/4. Okay, we're looking for R, and your half-life is 5730. P naughts cancel, so you're left with 1/2 is equal to e to the 5730 R. So we're going to natural log both sides. Okay, natural log of e is 1. So we solve for r like we did in the previous example. So we're going to divide by 5730. Okay, so I get negative 1.2097 times 10 to the negative 4. Okay, now I want to know, find the age of the fossil, so I'm going to use the formula again. And it says there were originally 133 and it's down to 60. So 60 is the final amount, 133 is the initial amount. Your R is negative 1.2097 times 10 to the negative 4t. Okay, so when we're solving this, we're going to divide by 133 first. Okay, and then we're going to natural log both sides. We natural log both sides, we bring the exponent in front, and we natural log the base. Natural log of e is 1. So what we're going to do is we're just going to divide. Okay, so we do natural log of 60 over 133, and we're going to divide it by negative 1.2097 times 10 to the negative 4. Oh, crap, I didn't. Natural log of 60 over 133 divided by negative 1.2097 times 10 to the negative 4. Okay, so I get 6580.18. 6580.182 years. Okay, and they actually use this for carbon dating when they're looking to see how old organisms were when they found the fossils and, you know, what time period they lived in. This is also used for nuclear physics, nuclear chemistry, and half-lives, and all that other good stuff. So another real-life application of exponential equations. We can also look at this to see what population growth is going to look like. Viruses, you know, how they're going to affect the death toll, that sort of thing, and modeling. So this has been using half-life problems and using POERT, or the PERT formula. So if you have any questions, feel free to reach out. Thanks, and have a good day.